Hello, welcome to this webinar on reflection and refraction. So we're going to talk about optical physics. So as you might know, light is a wave, but you don't always need to think of it as a wave, right? So depending on the situation, you will treat light as a wave, or you could treat it as a stream of particles. Or if you do quantum physics, you have to, you have to consider the quantum effects of light. And there are different areas. There's wave optics, for example. There's geometrical optics, and geometrical optics is where you can treat light as just traveling in straight lines. And so today we're focusing on geometrical optics. So this is everything to do with refraction, reflection, lenses, etc. Okay, so let's have a look. So geometrical optics is when the distances are much larger than the wavelength, effectively, the distances between points. So you don't need to consider light as a wave necessarily. And all right, so light travels in straight lines. An observer stands on top of a tall tower overlooking a perfectly spherical planet. Right, so we can draw that. We can draw a perfectly spherical planet. Okay, and there's a tall tower. So assume tall tower. And the observer's eye is 80 meters above, so it's an 80-meter tall tower, including the height of the human. So eye is about 80 meters above. And they're horizontal. So what does it mean to be horizontal? Well, horizontal means, well, look, parallel, perpendicular to the Earth's radius at that point. So basically, this line is considered the horizontal line. Horizontal. But the horizon, horizon is below the horizontal line. So if the person is looking this way, the person would see that the horizon is some angle below theta. In that case, theta is 4 millirads. So theta is 0.004 radians below the horizontal. That's what it means. And from this, we need to work out the radius of that planet. Okay, so this is the center of the planet. So we can draw a line like this. And this is exactly equal to the radius of the planet. And if we draw like this side, this side of the triangle is r plus 80. Right. If this is theta, then this is pi over 2 minus theta. And if this is pi over 2 minus theta, then this is also theta. And you can say that from this triangle, cos theta is r divided by r plus 80. And from here, we can make r the subject. So r cos theta plus 80 cos theta equals r. So 80 cos theta equals r minus r cos theta. In other words, r open bracket 1 minus cos theta equals 80 divided 80 cos theta. So the radius of the planet is 80 cos theta divided by 1 minus cos theta. And this is 80 cos 0.004 divided by 1 minus cos 0.004. We get something. We get some value. 80 multiplied by cos 0.004 divided by 1 minus cosine 0.004. Uh, 9 milli, so 9, oh no, it's 10. It's 10 million meters. So it's approximately 10 million meters, which is about 10,000 kilometers. That's the radius of the planet. For comparison, radius of the Earth is about is 6,400 kilometers, which is quite quite interesting, right? So all you need to measure the radius of the Earth is get your friend to swim into the sea until you stop seeing them. And if you measure the distance to that person, and then, yeah, you can find the radius of Earth. And actually, the first successful measurement of the radius of Earth was performed in, Greece or Egypt. Sorry, I'm a bit fuzzy on that. But they measured two sticks. They took a stick in Alexandria, I believe, and they measured the length of the shadow, and they came up with about 40,000 for 6,400 kilometers, which was very accurate for and that was 2,000 years ago. So okay, check who was the first one. It keeps like names. I'm not very good with names of who actually does that. Okay, so explain how a rain sensor works in a car. So you've probably seen those, or at least you have heard about them, that there's a rain sensor. Basically, when it rains, it switches on the windscreen wipers. So how does it work? Well, there's an LED, a light emitting diode, placed under the windshield. So here you can see two thingies. One is a LED, and one is a well, I don't know why it's called a photodiode. It's more like a LDR, light um, dependent resistor. Light dependent resistor. Basically, it's a light detector. It's something that doesn't have to be a photodiode. It could be an LDR simply. And the idea is that light reflects off the boundary between the glass and the air. So air, glass. Light reflects off the boundary, and that's how you know there's nothing on top of the glass. Now, if there was some water on top of the glass, water, then the light would not reflect. It would go into the water and escape effectively. So light would not reach the detector. So if there are droplets of water on top of the glass, light doesn't reflect. Right. So let's try to explain why. So bet bending light. Okay, so now when you go from air to water, you can see that some of the light is reflected and some of the light goes through. This is called refraction. Refraction and reflection. So when you have refraction, you always have reflection. You can see that 93.5% light is refracted, and of course 6.4% is reflected. Now, if you change the angle, you would see that this proportion changes. So 30% of the light is refracted and 70% is reflected. So depending on the angle. Okay. Now, when you go from air to water, you always have refraction. However, if you go from water to air, it's a different picture. If you go from water to air, yes, you have reflection and refraction. So you can see that 97 refracted, 2 reflected. But since of the angle of refraction is bigger than the angle of incidence, at some point, basically it reaches 90 degrees before this angle. So the angle of incidence just this is the angle of incidence, and this is the angle of refraction. Since the angle of incidence is less than the angle of refraction when light travels from water to air, and therefore R reaches 90 degrees before I reaches 90 degrees. Let's see what happens then. I keep increasing I, and then at some point, R just vanishes. It goes along the boundary, so only 5%, and then if I keep increasing, nothing. And you can see that 100% of light is reflected. So if the angle of incidence is greater than the critical angle, if the angle of incidence is greater or equal to the critical, then 100% of light is reflected. And this is called total internal reflection. Internal just simply means it reflects back into the glass or water. If you try to go from water, yeah, okay. And it turns out that if you use Snell's law, of refraction, and that this is the refractive index of water, refractive index of air. Snell's law is that theta 1, theta 2. So n1 sine theta 1 is equal to n2 sine theta 2. That's Snell's law. And for water, so suppose if n1 is water and n2 is 1, that's air, because the refractive index of air is 1, we know that. No, and then theta 2 must be 90 degrees. So remember, I've shown you, because when the angle of refraction becomes critical, and then theta is 90 degrees, and theta 1 is critical. Critical. So if you rewrite Snell's law for this case, n1, which is just n, multiplied by sine 1, sine theta 1, sine critical angle, equals n2, which is 1, multiplied by sine 90 degrees. But sine 90 degrees is 1, so that's equal to 1. In other words, sine of the critical angle is 1 divided by n. Is for the air-water boundary, or air, water, or air glass. For if for air boundary, and it's equal to critical is n2 over n1 for different boundary, for boundary between two media. And of course, because sine has to be less than 1, that means n2 must be less than n1. Otherwise, you just don't have a critical angle, doesn't exist, right? Because sine is less than 1. You can't have a sine which is more than 1, and therefore that's the limitation. So that's why they say you always have to go from a denser medium to a less dense, right? Means from denser to less dense medium. I'm sure in school you've learned, or at least you know some idea, so you know something about refraction. Okay, so what's going on with the light sensor, rain sensor? Sorry. Well, because when um, when there is glass, then the critical angle, glass and air, critical angle for glass air. So air refractive index is 1, glass refractive index is 1.5. Critical angle for glass air is, so sine C is 1 over 1.5. So C is arc sine of 1 over 1.5, which is approximately arc sine of 1 over 1.5, which is 73 degrees. 73 degrees. Is that? Yeah, okay. 73 degrees. So if this angle, if the angle of incidence, so if angle of incidence is more or equal to 73 degrees, it will reflect. It will reflect. Totally reflect. It will totally reflect. On the other hand, if there is water, N of water is 1.33. And then now sine the critical angle is critical angle is sine C is n1 over n2, which is 1.33. Sorry, n2 over n1. This is n1 and this is n2, which is 1.33 over 1.5. You don't have to remember which one's which. It's always the smaller one on top. Okay, the critical angle doesn't make any sense if you go the other way around. So the smaller one on top. Now, and C is arc sine of 1.33 over 1.5, and that is where did I get 73? My calculator is in degree, is in radians. I think that's why. 41, of course. I don't know where I got 73. Apologies. 41, 42 degrees, 42 degrees, 42. Angle of incidence is more than 42. And here, it's 1.33. It's 62. It's approximately 60, yeah, 62 degrees. And you can see that, well, if I is more than 62, if I is less than 62, then light will reflect, light will refract into the water, Now, whilst doing this problem, I realized one thing. I realized that light will refract into the water, yes, but it will also totally internally reflect from the water as well. And if it was a perfectly flat piece of water, then it will reflect back into the glass. But water droplets are not perfectly flat. They are actually round. So the light ray is very unlikely to return back into the glass. And actually, we'll be doing a question where we see that if we have several layers with different refractive indices, N3, N4, and actually the Snell's law can still be applied by just looking at the first and last layer. It doesn't matter what the refractive indices are in the middle. Well, if of course light is allowed to reach the other end. So if light reaches the other end, it will be the Snell's law will still apply with the first and last layer. We will see that with one of the next problems. Okay, so all you need, so light is shone between 42 and 62. And if it reaches the detector, then there's no rain. If it doesn't reach the detector, then it's wet. That's the gist. Okay. Does that make sense to you? Can you say something in the chat? Everyone's been quiet. Oh, thank you for the 9s. Yes. Okay. A transparent plate has a refractive index that varies continuously with depth. A light ray enters the plate at an angle but follows a curved path. So why would it follow a curved path? Well, because the refractive index changes and it changes continuously. So imagine you have you have a flat plate. Right? And there's the depth of the plate. The depth of the plate. And this is Z. This is 0. And this is H. And then at every section, N is different. N depends on Z effectively. Okay. And it says light enters the layer at a certain angle alpha. And then it follows the curved path. So we don't know how it changes, but in every layer it gets refracted a little bit. So it might as well just go like this, and then it will emerge at a different angle, beta. And yeah. So to understand this, let's consider glass with 3 layers. Okay. 3 layers. So this is N1, this is N2, this is N3, N4. So we can say this is N1, this is medium is N1, this medium is N2, and the refractive index inside changes continuously. So it changes from N1 to N2. And N2 and N5. So let's say we have 3 layers, but there's also the medium where the light is coming from. So if we have light coming through, so this is theta 1, and then there is theta 2. This is theta 2 and theta 3. This is theta 3 and theta 4. And then theta 5. Theta 5, theta 4, theta 4. And remember Snell's law. For the first boundary, we can write the Snell's law. So N1 sine theta 1 must equal to N2 sine theta 2. For the second boundary, so the angle of incidence is theta 2. Second boundary, N2 sine theta 2 must equal to N3 sine theta 3. This is just Snell's law. The third boundary, N3 sine theta 3 equals N4 sine theta 4. And for the fourth boundary, N4 sine theta 4 equals N5 sine theta 5. And you can see that this is equal to that, this is equal to that, this is equal to this is equal to that, this is equal to that, this is equal to that. So effectively, we have that N1 sine theta 1 equals N5 sine theta 5. Which is quite fascinating. So basically, light, we don't even know what N is inside the glass. We just know that it's a curved path. But for any number of layers, so we can extrapolate this for multiple layers. So what we're having here is we're having multiple layers. Multiple layers, and but for every layer it works. So it has to be that n1 sine alpha must equal to n2 sine beta. So where n1 is the refractive index of the medium on top, so the top medium and the bottom. So yeah. Now, if the refractive, you can have a situation where the refractive index reduces. Okay. Now, if light enters and then the refractive index decreases, let's say we can say that this is Z, this is Z, and this is 0. And the refractive index at any point, this is H, the refractive index of Z is equal to 0.1 Z, right? So it's proportional. The refractive index is proportional. So the higher you are, the higher the refractive index is. So when you enter the glass, you refract. But then as you go along, you refract away and away and away and away. So light will follow this path. But still, this rule will still hold. Theta1 and theta2 would still work, but because it's the same refractive index. So you come in, you bend in a circle because the high refractive index, and this is a low refractive index. It will refract away from the normal every time, and then it won't follow a curved path. So light can follow a curved path if in special circumstances. And to create, you can actually create these kind of circumstances if you take a big tank of water and you put a lot of sugar on the bottom, you'll have a concentration of sugar which varies with depth. If you don't mix, if you put a lot of sugar and if you don't mix, you would have sugar concentration varying with depth, and therefore the refractive index will also vary with depth. And you can use that to bend light in a curve. Okay. A monochromatic light travels from air to a liquid with a refractive index of 1.5. Okay, so liquid, air, liquid, and air is 1, liquid is 1.5. So light enters, that's theta1, enters the glass, sorry, theta, it enters the liquid. A mirror inclined at an angle of 20 at the bottom of the liquid. And there's a mirror, so there's the bottom of the tank. And then there is a mirror, which is placed like this. Mirror, mirror. So the light reflects off the mirror. And at this point, this angle, it doesn't exit. It doesn't go out of the liquid. So it reflects back into the liquid. So you must have total internal reflection at this point. So that angle, let's call it, if this is theta 1, this is theta 2. This is theta 3. This is theta 3. And this is alpha. And this is theta 4. So theta 4 must be greater than the critical angle. That's the condition. That's the condition in which light will not escape the water. So light enters and reflects off and then comes off, right? They're not saying the theta angle. Okay, theta light from air to liquid, from air to liquid, and theta 1. Ooh, let's do 40 degrees, perhaps. Yeah, 40 degrees is fine. Okay, so light enters, refracts. So first of all, we need to find theta 2. So for the first boundary, first refraction, you do n1 times sine theta 1 equals n2 sine theta 2. And therefore, you have n, and this is 15 degrees. Oh, no, so sorry, we're looking for theta 1. What am I doing? I'm being very daft. No, theta 1 is, we need to find theta 1. Theta 1 is question mark. All right. Okay, so for the first refraction, sine theta for n1 sine theta 1 is n2 sine theta 2. And that means that 1 multiplied by sine theta 1 is equal to 1.5 multiplied by sine theta 2. Or in other words, well, yeah, and we can keep that. Keep that equation, call it equation 1. Then reflection of mirror. Now, light comes in, reflects. So this is 15 degrees to the, this is 15 degrees. So this angle, if you consider the light to the vertical, this is theta 2, and this is alpha. So you can see that theta 3 is equal to theta 2 plus alpha plus 15 degrees. And then you can also see that this angle, theta 4, because this is theta 4 must equal to theta 4. So this is a vertical line. Oh, something's wrong. Theta 4 must equal to theta 3 plus alpha, which is theta 2 plus 2 alpha. All right. And now theta 4 must be greater than the critical, and the critical angle total internal reflection. For the total internal reflection, theta 4 must be greater then the critical angle, then sine, arc sine of 1 over 1.5, which is arc sine 2/3. Is it? Yeah, arc sine 2/3. Okay, brilliant. And now we reconstruct the whole thing. So theta 4 must be greater than arc sine 2 over 3. Theta 2 is equal to theta 4 minus 2 alpha, which is arc sine 2/3 minus 2 alpha. 2/3 minus 2 alpha. And then theta 1, so theta 2 must be greater, yes, than that. And then theta 1 must be greater than arc sine of 1.5 multiplied by sine, arc sine 2/3 minus 2 alpha. Yay! So theta 1 must be greater than, well, okay. Let's do theta. So theta 4 must be greater than arc sine 2/3. Arc sine 2/3 is 42 degrees, because we've already done that. 2/3 is 41.8 degrees. Theta 2 must be greater than plus 30. Must be greater than 71.8 degrees. And theta 1, or arc sine 1.5 times sine 71.8, and we get an error. Theta 2 minus, of course, minus, what am I doing? It's not 71, it's 41.8 minus, so it's going to be 11.8, 11.8, and then arc sine 1.5 times sine 11.8 degrees, which is 17.9 degrees. So if theta 1 is greater than 17.9 degrees, then the light will not escape from the liquid. So it will bounce back into the liquid, and that's it. Okay, so that's hopefully that makes sense. Number 5, next question. An object is placed in front of a mirror. Draw a ray diagram to locate the image formed by the mirror. State whether the image is real, virtual, upright, or inverted. Explain how the position of the image changes if the observer moves closer to the mirror. Okay, so let's take a mirror. Right, it's a mirror. Mirror. And this is an object. Let's say that this is an object. Object. We'd show it with an arrow just to show that it has a top and a bottom. This is an object. And how it works, that if we draw a line Let's draw a line from the top of the object to the mirror. And the light will reflect back to the object in exactly the same way. So light will bounce back. A different ray of light, let's say, a different ray of light will go from here, like this, and bounce off the mirror in that direction. And travel in that direction. So what does the observer see? So if you're standing here, what do you see, observer? You see two rays of light. You see the ray of light 1, and you see a ray of light 2. So you see two rays of light. And you ask yourself, where are they coming from? And because you know that light travels in straight lines, you think that this ray, the number 2, is coming from somewhere here. And ray 1 is coming from somewhere here. And the two rays intersect, 1 and 2, that's where they intersect, and that's where the top of the image is. So that's the image. If you do another one, if you consider the bottom of the object, so the image, this is, let's say point A, this is A dash, that's the image of point A. Now you can do any two rays. It doesn't have to be perpendicular, but I'll do it neatly. So one ray going like this, and another ray, and it reflects off the mirror. Thank you. Like a straight line. Reflects off the mirror roughly like this. And then another ray. Well, let's let it go like this, and it reflects off the mirror. Reflects off the mirror like this. So it goes like this, and your brain sees two rays of light, like ray 3 and ray 4. And where does your brain think that the light is coming from? Well, it thinks that it's coming from, this ray is coming from somewhere here, and this ray is coming from somewhere here. And this is where the bottom of your image is. So you think that the light coming from your brain thinks that light coming from the top of the object is coming from here. This is why we call it the image. Right, so this is how you form an image in a mirror. And this is the image. You can see the image is the same size as object. It's the same distance from mirror. And finally, it is upright. Well, indeed, if you stand in front of a mirror, you are standing the same way as your image. Now, it's really hard sometimes to convince yourself that the image is indeed the same size. I had this conversation with a colleague, a physics teacher at school, and he said, well, yes, the image is the same size as the object as long as the mirror is big enough. Because if you take a small mirror, you can place it and you can see a whole house in the mirror. So how do I convince you? Uh, well, you see my cupboard, right? The cupboard is obviously bigger than my phone. However, if I place my camera in such a way, uh, you can definitely see the whole of my cupboard fits inside that image. Does that mean that the image is actually smaller than the object? Because the object is the cupboard, and the image that you see fits inside a small mirror. Does it mean that the image is smaller than the object? That's a question for you. What do you think in the chat? Do you think the image of the cupboard is smaller than the cupboard? Okay. Why yes, why no? Can you try to explain, maybe? What do you think? You can. It's smaller visually. Mm, okay. Well, what I'm trying to do is I'll try to construct this uh, cupboard. So this is my cupboard. Cupboard. So my phone was roughly what? I was holding my phone about at the center. So I was holding my phone somewhere here. So that's the mirror. Mirror. And no, that doesn't make any sense. Uh, okay, I'll put the mirror right here. Okay. So this is the mirror. This is the cupboard. I think it's like seeing an object further away. And yes, you're bang on. Yes, it is exactly what it is. So if we construct light rays coming from the top, light rays coming from the top of the cupboard, it hits the mirror and reflects reflects I'm just gonna have to move the mirror slightly. And from the bottom, something like that. But if you draw the lines, so the light bounces off the mirror and into your eyes. So this is you, yeah? And it hits the mirror, but you think that the light is coming from all the way here. So the image of the cupboard, image of cupboard is exactly the same size as the cupboard. You're just looking at it from like through a window. Like if you can obviously see the whole of the cupboard, you can see my face through this little hole, right? The same way you can see the whole cupboard through a small mirror. The image is exactly the same, and if you draw a line through the mirror, the distance from the cupboard to the line containing the mirror, that distance is always the same. So D1 is D2. It has to be the same distance. So the cupboard is the same distance from the phone, from the plane containing the phone, as the image is from the plane containing the phone. If that makes sense. Right. So yes, always. It doesn't matter. The size of the mirror does not matter. It's just with a very small mirror, you don't see the whole image at once. You see parts of the image at different times. Yeah, if you take a small mirror, you don't always see the whole picture. The mirror creates an image of the whole universe, the whole half of the universe, right? You can't make a picture of the universe behind it, but the whole universe is inside that mirror. You're just seeing a small fraction of it. That's what's happening. Would it only change the mirrors? Yes, concave and convex mirrors, that would definitely change things. You can have a completely different images in concave and convex mirrors. Right, so that's that. So question number 6. A straight rod. Oh, I love this question, and I think it's the exact question from the assignment. So I'll try not to give away the whole solution. A straight rod is partially immersed in transparent liquid and viewed from above. Okay. So a stick looks bent when partly submerged in water. Just like this. Or like this. Is fun water tank head. No. Yeah, that's the one. It's not exactly related, but it's just, I love this picture. So yeah, you can see that a pencil appears bent when it is partly submerged in water. And this is a slightly different situation, but yes, this is refraction, where light is bent and the body appears to be in a different position than it really is. So let's come back to the pencil. Well, I'll leave it to you to draw how to draw the ray diagram for this situation. So homework, draw a ray diagram explaining the observation. Okay. Otherwise, let's focus on the pencil. So you have water, and you have a stick. And the stick appears, it appears that the stick is bent like this. Okay. Well, because it is viewed from above, then the end of the stick would be at the same position, right? Because the light from the end of the stick just goes directly upwards. So you could safely assume that it will just appear slightly shorter. And we can draw a vertical line like this. And let's call this distance h. H is the true depth. True depth. And h small is apparent depth. I realized I don't know how to spell apparent. Yes, that's what I thought. Apparent. Apparent depth. Okay, and now then this angle is, what does it say? The angle alpha. Alpha. And the bending angle, so the angle that the change of the angle, we'll call that angle beta. Beta. It's the change of the angle. So we need to maximize beta. So what alpha maximizes beta? Beta. That's the question we're trying to answer. So at what position does it look as bent as possible, effectively? Okay, and well, let's label this distance as I don't know, d, right? And this section of the stick is L. Well, I don't think we need that, just D. So we can say that this angle is alpha. So this angle is alpha. And this angle is alpha plus beta. So tan alpha, tangent of alpha is D divided by H. And tangent of alpha plus beta is D over H small. And in one of the problems, um, in the assignment, in one of the problems, is it's a coin. So the depth of the swimming pool problems in assignment. You will need to prove. We'll need to prove that h, the apparent depth divided by the true depth, is n1 divided by n2, is the ratio of the refractive indices. And we know that n for water is 1.33 and n for air is 1. And therefore, h over h is 1 over 1.33. Or in other words, h is 1.33 times h small. Okay. So what we do here, we divide them. So tan alpha divided by tan alpha plus beta. And that's equal to h over h. And that's is actually 1 over 1.33. So tan alpha is 1.33 tan alpha. Oh, I don't know why we just n and h. Let's not carry numbers. N, so n tan alpha equals tan alpha plus beta. Okay, well, it looks like we'll need to use trig identities. N tan alpha is equal to 1 plus tan alpha tan beta tan A plus B identity. A plus, okay, that's A plus B. B1 minus, is it minus? Yes, it's minus 10. Tan alpha, tan beta. Does that make life easier? Not particularly. But okay, let's still do it. N tan alpha equal minus n tan squared alpha tan beta equals tan alpha plus tan beta. And we need to maximize beta, right? So we can take tan beta to one side. Tan beta, open bracket, of 1 plus n tan squared alpha equals n tan alpha minus tan alpha, tan beta equals n tan alpha minus tan alpha, and divided by 1 minus plus n tan squared alpha. I'm gonna make some substitutions. Substitution. X equals tan alpha and y equals tan beta. And this way I can write y equals n multiplied by x minus x divided by 1 plus nx squared. I really hope I haven't made a mistake anyway. And because I need to maximize, I'm going to differentiate. You know, Why not? Differentiate. Y dash is equal to, to differentiate the top, it's going to be n minus 1 multiplied by 2xn minus n minus 1 x multiplied by, oh, what am I doing? Made a mistake. I'm using the quotient rule here, so 1 plus nx squared, n minus 1 multiplied by 2nx, yes, all over 1 plus nx squared squared, and I can simplify that, and this becomes n plus n squared x squared minus 1 minus nx squared minus 2n squared x squared plus 2nx squared. N squared x squared cancels. Divided by nx squared squared. That's going to be n minus 1 minus 2nx squared, open bracket, n minus 1, 1 plus nx squared squared, and that is n minus 1, open bracket, 1 minus 2nx squared, 1 plus nx squared squared, and then it must equal to 0, because at optimum there's 0. But we know that this is not 0 because, well, n is not 1. We don't care about the bottom, so it's 1 minus 2nx squared must equal to 0. So x squared must equal to 1 over 2n. That means that tan squared alpha, yeah, is equal to 1 over 2n. So alpha must be arctan of square root of 1 over 2n. I really hope I haven't messed up. Oh, the correct answer should be arctan 1 over n. You can sort out n squared and nx squared. Yes, I have. Okay. Thank you for that. This is going to be n minus 1 minus n squared x squared plus nx squared. We don't care about the bottom. Yeah, n minus 1 minus n minus 1 x n minus 1 x squared n. Yes, yes. And that's equal to 0. That means that x squared n is equal to 1. So x squared is 1 over n. So tan squared alpha is 1 over n. Alpha is arctan of 1 over n. Oh, thank you. Thank you for... I'm actually surprised that I haven't messed up more in this one. But yeah, here you are. Here's a solution. You differentiate that. You substitute and you differentiate, and that's how you optimize. So pretty neat. Can I get an honest an honest view of understanding of how I did it on a scale of 0 to 10, please? Don't worry. I mean, it's if I give this if I give this question to a cohort of the top 10% of UK's year 13 students, if I take the top 10% of the UK student, I would bet that 70% of them would not be able to do it. So to do this question, like I'm almost certain this is way harder than any question you might be asked on a Oxbridge interview, for example. Okay, so don't worry if you don't get it. It's absolutely fine, but if you do. Right, so number 7. Uh, okay, not way harder, but considerably harder. Like than physics Oxbridge interview. Right, so a light ray travels from point A to point B in water, refracting at a flat interface using Fermat's principle. So Fermat's principle is a principle of the quickest path. And this is one of my favorite things to consider. So imagine you have a boundary and you have a ray of light entering the boundary, and there is an angle θ1. And then it reaches. So light travels from point A to point B, and it hits the boundary at point C. The refractive index, so it's N1 and N2. And maybe I haven't mentioned it, but the speed of light is equal to speed of light v is equal to c divided by n, where c is the speed of light in vacuum, and n is the refractive index. And therefore, we know that the speed of light is c over n1, and the speed of light here is v2 is c over n2. We'll take 2 triangles here. And yeah. So we need to go from point A to point B in the quickest possible path. So aim, go from A to B in the quickest possible path. So let's say that this distance is L, big L, and this distance is X. So basically, we're solving for X. We're solving where the light ray should hit the boundary in order to go to B in the quickest possible way. So basically, in this medium, this is a fast medium, and this is a slow medium. You want to spend more time in the fast medium and less time in the slow medium. So that's why your path has to be bent. So you're solving for X, where X is where you hit the boundary. And well, this distance, let's call it h capital, and this would be h small. Do we actually need it? Well, maybe. Okay, doesn't really matter. Now, this distance AC, the distance AC, is the square root of h squared plus x squared. And BC, CB, this distance, CB, well, this is L minus X, of course. CB is the square root of L minus X squared plus H small squared. And we want to minimize the time. So time to travel from A to C is going to be AC divided by speed. So AC divided by V1. So there's going to be square root of h2 plus x squared over v1, which is c over n1. And time to go from c to b is going to be cb divided by v2, which is square root of l minus x squared plus h squared divided by c over n2. So total time, t total, is going to be square root of h squared plus x squared divided by c multiplied by n1 plus n2 divided by c square root of l minus x squared plus h squared. And now we differentiate to find minimum, to minimize t total, we differentiate. So we're allowed to change x until we get a minimum. We differentiate. So dt total by dx, we differentiate with respect to x. So we find the derivative. So n1 over c. So we use the chain rule here, multiplied by 2x, multiplied by h squared plus x squared to the power minus a half, plus n2 over c, multiplied by 2x minus 2l multiplied by, oh, where did it get the 2? Oh, we need a half. So multiplied by a half, multiplied by l minus x squared plus h squared to the power minus a half. And that must equal to 0. Okay, be brave, lad. 2 cancels. 2 cancels. We get n1 over c square root of h squared plus x squared plus n1x, n2 x minus l over c multiplied by square root of l minus x squared plus h squared. Okay, and that must equal to 0. We can remove the c's. Oh, we can take one to the other side. So we get n1x over h squared plus x squared must equal to n2 L minus x square root of L minus x squared plus h squared. Oh, I think I've outdone myself because actually I don't need to go any further, because if I go back here and look at this triangle, this angle is theta 1, and this is the hypotenuse. So sine theta 1, but sine theta 1 is x over square root of h squared plus x squared. Yeah, sine theta 1. I'm just going to write it down here so that you can see what I'm talking about. Sine theta 1 is the opposite, so x divided by the hypotenuse, which is square root of h squared plus x squared. And here, this is theta 2, and this is theta 2. So sine theta 2 is equal to L minus x divided by square root of L minus x squared plus h small squared. And if I take that and put it here, you can see that here it is. Oh, and here it is. Here's the sine. So that's just sine theta 1, and this is sine theta 2. And what I've just shown, that using Fermat's minimal time principle, so n1 sine theta 1 must equal to n2 sine theta 2, which is Snell's law. So Snell's law can be derived from Fermat's principle, which says that light should take the minimum possible time to go from point A to point B. That's why light travels in a straight line normally, because the straight line is usually the quickest path. If it's well, if you differentiate the minimum or the maximum, it's certainly not the maximum. I mean, all right, yes, I haven't. You can find the second derivative and say differentiation gives the minimum or the maximum. You can easily show that it's not the maximum. Right. You're still not convinced? At the maximum point, you have the derivative is 0, of course, and the minimum point, the derivative is 0. You can find it. There are different ways, of course. I omitted that bit. Okay, you will learn that as you go along in your studies. In optimization problems, they are usually not required to show that it's a minimum or a maximum. You just need to find the derivative, because there will only be one option. Then, if you want to show that it's a minimum or maximum, well, you can take the second derivative. That's one way of doing it. Or you can just plot the graph and see that it is a maximum. Or you can take a small change. If you can change x slightly, make it slightly less, make it slightly more, and you will see that it is a maximum, a minimum. So you would see. So if this is the optimal, this is x optimal, then any value here would be higher. So this is x optimal minus small epsilon, and this is optimal plus epsilon. So the value of x optimal minus epsilon is going to be greater than f of x optimal. Also, f of x optimal plus epsilon is going to be greater than f of x optimal. And that's how you can show. So you go from the optimal point, from the minimum, you go slightly to the left, and then you will see that you get a bigger value. If you go slightly to right, you get a bigger value, and that tells you that it's a minimum. That's another way of showing it. Or using the second derivative must be positive, or the second derivative must be positive. Cool. Right. I'll stop here. Thank you for your attention. So I will see you. Let me just double check. And webinars, year 11. So the next webinar is 17th of February on Euclidean geometry. So see you. I'll see you then. Enjoy. You're welcome.